Hello, and welcome to the talk about zkEVM, the technology that will extend zk rollups from application-specific functionality to generic programmability. This has been considered a very difficult task, and it was in fact impossible up till this year. And many people thought that it will not arrive up till a few years from now. But I'm CEO and co-founder of Meta Labs, the company behind the ZK Sync protocol, and I can attest that zkEVM is coming to Ethereum this May on the testnet and in summer, hopefully to production. And in this talk, I'm gonna go into the history of the ideas behind generic computation and zero-knowledge proofs, and we'll demonstrate why it was not possible, what changed, what breakthroughs actually make it available for us today. And hopefully I'll be able to give you a good intuitive understanding of its design. I will assume that you have some basic zero knowledge proofs understanding. If not, please watch other videos. We don't have time in this 20-minute talk. Let's start by recapping quickly how ZK rollups work. We have a state of our blockchain or a rollup with some accounts. They have some balances, some data. They are packed in the Merkle tree. We have a root hash of this Merkle tree serving as cryptographic commitment to the state. And whenever the state changes, because we apply one or more transactions to it, the root hash will also change. And we can define the transition with a so-called state transition function. So whenever we have a block, the new root hash will be a result of the state transition function from the previous root hash, the transactions data that are involved in this block, the accounts that are modified by those transactions, and the Merkle proofs for these accounts. And this is all information we need to construct a new root hash. This is, in fact, what you would place in a stateless client to verify a block. So if we only could implement the state transition function as a zero-knowledge proof, this would allow us to implement any type of ZK rollup. And we actually have this. So ZK Sync is live on mainnet since June. It's being used for payments very actively. And we have the very efficient provers, very efficient arithmetization techniques, that is frameworks that convert the algorithms in the state transition function into the form which is digestible for zero knowledge proofs. We have all the server infrastructure around it, the smart contracts. So all we need to do in order to support generic computability is to make sure that the generic smart contracts can be efficiently arithmetized. And this is a big challenge. So arithmetization is a process of converting the function into what we call an arithmetic circuit. It's a directed acyclic graph where the inputs of your function are the initial nodes, and then you go through a sequence or through a network of gates. Each of the gates represents an operation of addition or multiplication in a finite field, and eventually you keep accumulating your results and you get to the final output. And you can imagine it can be pretty complex if you have a big algorithm. So something like simple arithmetic operations are very cheap. You can do them with one gate. Logical operations will take more gates. Hash, such as SHA-256 or even Ketchup, will take a lot more of those gates. But that would be doable. The problem we have, or the challenge we have, is how to make it generic. Why is this a challenge? If you're familiar with your knowledge proofs, you know that the verifier, which in our case is a smart contract on Ethereum, must know in advance the circuit. So the circuit must be fixed. You know, you can't change it on the go. You define it once, then you make some computations to generate a verification key, and then you use this verification key to check the proofs. Now, with generic smart contracts, we want the users to be able to define the contracts and deploy them on this chain permissionlessly, which means we cannot rely on a single static, rigid arithmetization of one like fixed state transition function. So we need to find a way how to have multiple contracts coexist. So let's go through the history of ideas that were tried in this area. We will start with an approach called TinyRAM, which is already 8 years old. And this is a really fantastic idea. It solves the problem by saying, let's create a circuit which verifies not an execution of a single, like a single algorithm, but let's make a circuit that can verify any algorithm by verifying the execution trace of the program. The way we do it is we assume that we will have n steps of execution. You can think of them as the cycles in the processor. And at each of these steps, what we're going to do is we will read the inputs and the opcode from the program counter. And we will do all of our operations. And then we will select the result of only the one operation which actually is supposed to be executed at this step. So this gives us a quadratic complexity, or like number of steps multiplied by the number of operations. And the number of operations must be relatively small. So we would go for something like RISC architecture with a small number of opcodes, which must be relatively equal in cost. We could then prove anything. How it works, to give you a bit better, more intuitive understanding, I made this model in a spreadsheet. Let me show it. Imagine that I want to write a program. So I want to turn this spreadsheet into a universal interpreter of a program. And I will provide my program here in the yellow columns with the type of operation at each step and the operand. And I want this program to be executed every time sequentially. So each step must be applied to the result of the previous computation. We will start with accumulator with a value 0, for example, and then I'm going to add 13, subtract 5, multiply this by 3, and so on. So we're going to support 3 operations: add, sub, and move. And as you can see, when I change something here, all of the computation changes, starting from this step. And finally, in this cell, we will have the result of our computation, of the application of all of this program. So the interesting thing is, I can modify the program and I can modify the inputs, but the spreadsheets itself, the formulas, or essentially the circuit which I use to produce this final outcome, remains the same. And if you look at how I constructed this circuit, at each step, I do a simple computation. It's the same computation for all of them. And it's just a simple formula which does the execution of all 3 of our operations: addition, subtraction, and multiplication. And I use this simple naive approach to select just one of them, right? So like if the operator is add, then I will just take this result, right? Because I will multiply it by 1 and not by 0. If the operation is sub, I will take this result, mul this result, and I just add all of them, and I get only one outcome. So like this is how TinyRAM works. So in this example, we have here only like static problem without jumps, without comparisons, without memory access, but all of them are possible to implement. We have some very efficient models that could be used for TinyRAM. The problem is that it's gonna be pretty expensive. If you compare a program written, like handwritten as a circuit, to a program which runs in a TinyRAM circuit, the TinyRAM must be approximately 1,000 times larger in terms of the number of gates in order to accommodate this program. And for some simpler cases, for simple computations, this will work. And even for some, Yeah, actually, even for simple hashes, it will be already too expensive. But for hashes that are required for EVM, it would be prohibitively expensive. Like we won't be able to support it. The cost will blow up immensely. So this doesn't work. It's been there for 8 years, but it remained a very theoretical approach until recently, because like not usable. So we looked at this 2 years ago, and we thought, okay, what if we use the recursive aggregation? It's possible with zero-knowledge proofs to construct a circuit which verifies a proof of a different circuit. And we can dynamically load the verification key, so we can verify circuits of different types. There were approaches to this. The main problem was the cost of constructing such a circuit, which was solvable by using cycles of elliptic curves. So we could have like each user will define their own circuit, or like each developer of a smart contract will define their own circuit, publish it on the rollup, and then the users will take the circuit, provide the proofs, and then the aggregator will take all of them in the block and produce the proofs of intermediate results. It can be nested many times in a tree-like structure until we get to the final proof of the entire execution of the block. The problem was that cycles of elliptic curves were not available for efficient computation on Ethereum because we lacked the precompiles. We only have a precompile of BN256 on Ethereum. This is the name of a curve we use. And BLS is coming soon, but nothing that supports the cycles of curves. So our first solution to this was 2 years ago to come up with EAP 1962. We implemented it at Meta Labs with we produced two different independent implementations, one in Rust, one in C++. We made a lot of testing, fuzzy testing, a lot of discussions with ETH core devs. But eventually the community deemed this to be too risky back then, and like too big a precompile to include, and it never got adopted. And I can understand that for a project like Ethereum, being more on the conservative side with regard to what's going on the mainnet is perfectly justifiable. So, okay, we thought, what can we do else? And last year, the Aztec team came up with a number of interesting ideas on how you can structure elliptic curve arithmetics in a Plonk circuit in a more efficient way. We looked at that and we thought this is a perfect candidate for us. So we went ahead and implemented the first recursive snark on Ethereum using Plonk. We submitted it last summer in August for the Reddit scaling challenge. And we actually implemented it in production and launched it in January this year for our ZK Sync rollup for payments, which made the this rollup indefinitely scalable. So we are now only limited by Ethereum block size for data availability, but not by the zero-knowledge proof computations, because we can construct this tree with as many blocks, like smaller blocks of rollup as we need to submit on Ethereum and verify in one single check. The problem with this solution is it's not Turing complete. It required us to implement a new programming language. We called it Zinc. It was Rust-based, and you would need to rewrite your programs in a certain way. You would need to avoid unbounded loops, avoid recursion, and also think about how you structure your branching, because if you have too many nested branches, all of them would have to be executed, and it could blow up the complexity a lot. We thought, okay, for most DeFi applications, this is probably not going to be a problem. They are not as complex. They do not require that many computations. A lot of programs are written in Viper, which is also a non-Turing complete language. But then we realized that people actually really want Turing completeness. People wanted to have EVM. We got this market signals that people really wanted to take existing programs written in Solidity, reuse the tooling they have, reuse the audits they already invested heavily into, and just like not need to learn a new language and rewrite stuff. So we thought, okay, what can we embrace this challenge and actually implement it? So we looked at the third approach, which would be, what if we could optimize TinyRAM to make it more efficient for this specific use case? And what brought us to this idea is this observation. If you write a smart contract in Zinc, like manually handwrite a circuit for it, then the smart contract logic itself would take a very small fraction of the prover cost structure. And the bulk of the proof of costs will go towards access to memory, access to storage, signatures, hashes, other heavy operations. So if we could apply TinyRAM to this small fraction, to the actual contractual logic, then even 1,000 times overhead would not be a problem, because overall it will not make a big impact on the prover costs for this transaction. Like maybe it will just increase it twice, or maybe by 30%, by 50%. And the heavy operations, we could write specialized circuits for them. And what we could do is like take our TinyRAM circuit and split it in parts and have one part for actually TinyRAM with execution of arbitrary trace of opcodes, and then have signatures and hashes done as separate parts of the circuit, which can be addressed by these operations. Now, the problem with this approach is you can't really have too many of these specialized operations. Like you have to maybe you need to pick one or two, because otherwise it's an impossible optimization problem to pick like what fraction of the circuit should be reserved for each of the operations. Because if you just reserve equal number of gates for like for storage access and for cache hash and for SHA-256, then it would be very inefficient if some block does not utilize all of it, because the blocks and transactions are very heterogeneous. Like one transaction might require a lot of storage accesses. Another transaction does a lot of EDDSA signature checks, so you need a lot of cache hashes. And yet another transaction uses SHA-256 for some reason. So like it's not clear how to like dispose it. And this is why it's not suitable for zkEVM. It is suitable for generic programmability. So you could write a separate language and force developers to think about it and make certain trade-offs and like only have hashes, for example, and build everything on top of cryptographic hashes, like not KCHAC, not SHA-256, not Ethereum compatible. And I think this is the only approach which you can do with Starks. And this is very efficient with Starks for the reasons of how Starks are structured. But it doesn't allow us to make zkEVM, and this was the goal. So we could not go for this. And this brings us to the final approach, which we actually implement in zkSync 2.0, which is a combination of TinyRAM, optimized circuits for specific heavy operations, and the recursive aggregation of all of it. And the way it looks like is this. We have transactions, like users submit transactions in form of, or like smart contracts in form of bytecodes. We have separate circuits of different length, structured by powers of 2, for the execution of the TinyRAM part of those contracts. And then we delegate all the heavy operations to specialized circuits, which are then aggregated recursively along with all the proofs for the transactions. And if we need more of KCHAC hashes, then we just add more of these circuits to the mix. If we need more storage, we just add more storage. If we need more EDDSA signatures, we add more of those circuits. And we can efficiently aggregate any number of them, the way I described before, to get the proof of the execution of the entire block. And we also heavily optimized the specialized parts over the course of the last year. So we added specific things for 256 bits arithmetics, We have very efficient snark-friendly hashes. We have pretty efficient non-snark-friendly hashes as well, because we take advantage of the Plonk's custom gates and lookup tables, and this gives us a boost of 10x or even more in some cases. So we can do it very efficiently. The way things work with zkEVM is you take your code written in Solidity, for example, like the language you compile it with your normal compiler into U, and from there we have an LLVM-based compiler using a lot of optimizations from LLVM. It's a great platform for compilers to produce the zkEVM bytecode, which you can then permissionlessly deploy on the ZK rollup and execute. And we actually have done a simulation on we took the transactions from L1 for some frequent DeFi use cases. We fetched the execution trace and we looked at what the prover cost will be in this case for us, like with overall costs, with recursion, with the heavy operations, with the tiny RAM part of it. We came to the prover costs of like 1 to 2 cents for any transaction we analyzed, which is very doable. And on top of that, you will have to pay the cost of data availability, which depends on the gas price. If you use ZK Rollup, if you use something like ZK Porter, our alternative approach to data availability, that's going to be a lot less. So you will overall pay only like 2-3 cents for a transaction on a ZK Porter. But this is your base cost, and we like this scales a lot. So as I said, this is coming to testnet in May and hopefully to production in summer. And we have a few minutes left. I'm happy to answer any questions. Thank you.